So here's what I'm thinking. I'm thinking that you want a table that shows maybe a quick little picture of a functional group, a quick little maybe description, but then we're going to have a column to have a place to describe some of the properties, physical and chemical properties. Not going to get into that in this video. We're just going to go through the list of functional groups. But this is a pretty boring background. Let's see if we can fix that one up. Yeah, that's a little better. Not a lot better. It's still kind of dull, but it's a little bit better than what we had. All right, functional groups then. First of all, we need to know what a functional group is. Now, you may already know this. You may not. If you do, awesome. If you don't, here's what it is. It's a grouping of atoms, or it's a particular type of bonding between atoms. And what that's going to do is it's going to allow us to classify the compounds as belonging to this family or to that family. And those pairings, either the groups of atoms or the types of bondings that they have, are also going to, in some cases, or at least partially, determine physical and chemical properties. So we know that, say, certain things are more reactive than others, and that's oftentimes based on the functional group. Now, there's a lot of other things involved in that, but as a general pattern, we can say that these things are a little bit more soluble, these things have a higher boiling point, these things are more reactive with acids or something like that. The functional group, and that's also, for us, the big part is going to be determining nomenclature. How do we name this thing? Okay, so those are the key things about what a functional group is and what it does for us. So what are the functional groups? So the first one, in some ways, really isn't its own functional group because it's the if there's nothing else there. So the alkane only has carbon and hydrogen atoms, so it's called a hydrocarbon. And all the carbon atoms are single bonded, which means carbon single bonded to a carbon. And the first one there, you'll notice, has no carbons bonded to carbons. It's just a single carbon. That's the simplest alkane going. Now, what you're looking at here is considered to be the expanded view. Normally what we do is we write the condensed view like this, and we don't condense it much more than that. And that'll make a little bit more sense when we move on. If you had a carbon chain that had more carbons, well, now we start to have something a little bit more obviously an alkane, where we've got a carbon-carbon single bond here. Now that is not a complete structure, and we might draw some version of this, but we'll never leave it like this. So make it real clear right now, you will never draw a skeleton structure like this and leave it like that. We will always include the hydrogens. Now, one of the key features about all organic compounds is that every carbon has 4 bonds. And you can see that very clearly in this structure. It's a little bit less clear in this structure, but this carbon right here is bonded once, twice, and then it's bonded to 2 hydrogens. So if I were to expand this structure out at this point, it'd be a carbon, that carbon, and then a hydrogen and another hydrogen. Now, we don't usually do the expanded view once we get into larger molecules, so we have it looking more like that. But we always make sure every carbon has 4 bonds. You can also have those carbons attached in a ring, where this one, the carbon to a carbon to a carbon, all those single bonds, go around in, well, not quite a circle, but basically go around in a circle. And we could write it in this condensed view. There's a shorthand that we will typically use for rings, and where the point represents a carbon atom and the line represents the bond. And then those hydrogen atoms, we just assume that are there. Now, I don't really want you using this real shorthand notation on chains. Once you're a little bit further on, once you're, third year university, when you're doing this professionally, fine, go right ahead. But where we're starting at right now, don't take the shortcuts. Alkenes. We should be able to go through alkenes a little bit faster because we have a couple of basic background things taken care of from alkanes. Alkenes also are hydrocarbons. Alkenes, though, have a carbon-carbon double bond. And please don't look at this as a carbon equals carbon. It's a carbon-carbon double bond. And you'll notice that along the chain, whatever that chain is, there will be a carbon double bonded to a carbon. Now, if I can just draw this in expanded form a little bit more, do that quickly, that would be the expanded form, which we condense down to the view that you see here. And it doesn't matter how long that chain is, as long as there is one carbon-carbon double bond, it's going to be an alkene. So even though there's all kinds of alkane sections within this molecule, it's still an alkene because it has that double bond. Alkyne, also hydrocarbon, but is carbon-carbon triple bond. So we said functional groups are either going to be groupings of atoms or bonding patterns. So we're into the bonding patterns right now. A triple bond, carbon-carbon triple bond, and again, like the alkene, it doesn't matter how the other, what the rest of the chain looks like. If it's got a carbon-carbon triple bond, we're going to be calling that an alkene. Alkyl halide has a halogen atom. Most commonly chlorine, sometimes bromine. Iodines and fluorines are less common. And for our purposes, when we're drawing structures and doing nomenclature, just for getting you to use the things, more often you'll be seeing chlorine and bromine. Most often chlorine. Now, one of the things, again, this is just strictly recognition. If you kind of look at this group here, the CH3, and this piece here, that's the chlorine. Taking a quick glance at it, sometimes kind of hard to see. So we do have to be paying attention all the time. And here's one with the bromine. Again, bromine on the end. We tend to start looking at these things and glance at it really quickly and think we see stuff. But there's an alkyl halide, and there's an alkyl halide. Alcohols and ether are going to stick together. They're sometimes considered to be organic derivatives of water. Now, what does that mean? Well, if I start with thinking about water, where it's an oxygen bonded to two hydrogens, if I replace one of the hydrogens with a carbon group of any length, I've got one carbon here, but this could be 2 or 3 or 4, then it's an alcohol. If I replace the other hydrogen with a carbon group, now it's an ether. And again, this could be more carbons down the chain and so forth. Alcohols and ethers also have their own unique properties, like all the other ones. We'll deal with them individually, or you'll get a chance to write that down. For our purposes, most of our time is going to be spent on the properties and the nomenclature of alcohols. Ethers, not so much. I do want you to be able to recognize them, but outside of recognizing this thing as an ether, that's about the only thing we're going to be dealing with. Amines. They are organic derivatives of ammonia. If you think back to grade 11 nomenclature, that's ammonia. If you look at the structure of ammonia, I guess I should have a couple of dots there for my electron pairs. If I start replacing hydrogens with carbon groups, I now am building up amines. Now, quick little difference between what we had in the previous one. All of these are amines. I remember before, if I took one of the hydrogen groups, it was an alcohol. If I took the other one, it was an ether. This doesn't change functional group. They remain amines the whole time. We're going to do very little with amines. We're not going to look at the nomenclature of them, not really, and we're not really going to spend that much time with the properties of them. But we can have amines that are hanging off the chain. We can have amines that are in the chain, and you'll notice that these two are fairly similar, and these two are more similar. Okay, just because of where the nitrogen sits. Where's my? There we are. Aldehyde and ketones, these will be important for us. They have what's called the carbonyl group. Now, I'm not going to start breaking down functional group recognition and start talking about a hydroxyl group or a carbonyl group, but you're going to hear that term, particularly if you take biology. I know that the biology section, they start talking about carbonyls and things like that. For us, we're going to call this either an aldehyde or a ketone. What's the difference between them? Well, if they both have a carbonyl group, it's where they are on the chain. So an aldehyde happens right at the end. So this carbon of the functional group right here is attached to a carbon on one side and a hydrogen on the other side. So this is our key feature in recognizing an aldehyde. Whereas a ketone, carbon of the functional group, so there's my functional group, carbon on the left, carbon on the right. Doesn't have to be a single carbon, it can be a carbon chain. Can also, and this is a little harder to see because I'm using that very short form, but here's the carbon of the functional group, carbon on the left, carbon on the right. Ketone. Carboxylic acid, a little bit hard to pronounce it off when you first see the name. Carboxylic acid. It's an organic acid, which is no big surprise. It has what's called a carboxyl group, probably no big surprise, and that carboxyl group is a carbon double bonded to an oxygen, single bonded to an OH. So some people, when they first see this, think that it's somewhere in between an aldehyde and an alcohol, but it's not. It's its own group. So now when I'm looking at functional groups or I'm identifying functional groups, I have to start expanding. I have to start looking a little bit further down the line a little bit. So much like an aldehyde, a carboxylic acid has to be right on the end of a molecule because it only has a carbon on one side of it. Ester, I didn't spell it wrong. The ester with an H is somebody's name. Ester without the H is a chemical functional group. And it's sometimes considered an organic salt. Now, if you're writing things down, which is awesome, you don't really have to write this down, but just trying to put it into a bit of a perspective for you. You're never going to really need to know that part of it. So here's the functional group. Carbon with the double bond oxygen, followed by an oxygen. So now we started out with sort of a ketone aldehyde look. Now we're into acid look, and followed by a carbon. So the whole functional group is right there. Carbon, double bond oxygen, followed by oxygen, followed by a carbon. And the carbon line can be shorter or longer, as well as the carbon line on the other side of the acid. What people sometimes get used to seeing is this, but if it were the other way around, let's go try that again. Nope, not that one. If it were the other way around, followed by that, what happened there? We're doing well today. That's also an ester. Hopefully I can edit that out, but I have a feeling I can't. So that's an ester. Doesn't really matter. This is an ester. So there's a carbon, double bond oxygen, followed by an oxygen, followed by another carbon. I must be pushing a button somewhere. Followed by another carbon. Okay? That's easier than what I'm trying to do here. There. And finally, amides. Amides are this. So we've got the carbon double bond oxygen, followed by a nitrogen. So kind of in the between, bringing in the amine side of it, but an amide. Again, not going to be a big part for us, although I do want you to think ahead if you are taking biology, because this bond right here in organic chemistry is called an amide bond. In biology, it's called a peptide bond. And if you were to look at this thing here, where I have an amine group on one side, an acid group on the other side, that in biology is called an amino acid. And once I start linking several amino acids together, so here is one, kind of cutting between here, here's where the next one starts, here's where the next one starts, and then this one still has the OH group. You'll notice the OH group is kind of got used up in the bonding. This, in each one, is the amide bond or the peptide bond, which is called in biology, but this is the beginning of a protein. Okay, so they are really important, it's just they're not going to be important for us. Much more important in biology. That's your basic functional group. We're going to have a couple things to do with that. Number one is functional group recognition, where you'd come along and say, this is an amine, this is a carboxylic acid, and this is an amide, stuff like that. You would circle the functional group, identify what kind of functional group it is. And we'll be doing that for a bunch of things, even when there are multiple functional groups. Second thing we're going to have to do is name things like this. Now, we're not doing the nomenclature yet, but name compounds like this. This one's kind of complicated. We won't be getting into that big. But identifying the functional group is an important part of naming the compound. Anyhow, that's functional groups in a nutshell. Talk to you in class.